Hi, everyone, and welcome to this webinar on advancing net zero through just energy transitions. I'm delighted that you can all join us. And before we kick off today's session, I'd like to bring in Professor Tim Lenton, who is the founder of the Global System Institute and the chair in climate change and earth system science at the University of Exeter, and also a director of the Economics of Energy Innovation and System Transition, or EEIST, which is the program that's responsible for the research that we're going to be discussing in today's webinar. So Tim, over to you for a quick introduction.
Hi folks, I hope you can hear me because I'm on double Zoom here due to a kind of technology crisis, speaking to you from New York's Climate Week. Let me try and make it less freaky by getting rid of one of my video settings. Sorry, there we go. So yeah, I think I was just asked to give a few words about how what you're going to hear about today kind of fits in where the discourse is here. So in New York Climate Week, I've been on behalf of the project and with other colleagues really pushing the message that exponential change is the expectation and the reality for the energy transition and the associated mobility transition to electric vehicles. It's still the case that, shall we say, major actors in the financial sector and other governance actors are thinking in a linear way about the transition and the transformation. But I think we've seen this week in New York that when you show them the data of what's actually unfolding, the penny drops, and everybody and people's expectations and understanding now is really shifting. That the default assumption should be that we are in the exponential growth phase of what will be an S-curve in the power sector in electric vehicles, and we've got the signs that we're starting those S-curves in a number of other key coupled sectors. And we need to get away from this language that those are optimistic projections and rather say that we should be expecting S-curve dynamics and all of the important ramifications that come from that, which we're going to discuss in the seminar today. So that's really my prelude to what I hope will be a great set of short talks and discussion. Thanks.
Great. Thank you so much, Tim, for that great introduction. And hello again, everyone. I'm Anupama Sen, and I'm Head of Policy Engagement at the Smith School of Enterprise and the Environment here in Oxford. And I'm delighted again that you can join us for this session. So just to give you a quick run through of today's agenda, today we'll be discussing the results of new analysis from the EEIST project, which Tim's just introduced, based on 2 new policy briefs which have just been published today and which are the result of a longer research project and a number of underlying papers on new economic modeling approaches to the energy transition. So we're joined by the authors of these briefs and also by 2 expert discussants. We'll start off with 3 short presentations from our 3 authors. The first one will be on new economic modeling. The second will be on the socio-economic impacts of the coal transition in China. And the third will be on the role of green hydrogen and ammonia in a low-cost resilient power system in India. And after each of these presentations, we'll bring in our expert panelists to give us some reflections on the results. And we'll also open it up to audience questions and discussion. So to our audience, please remember to ask questions using the Q&A function in Zoom, which you should see at the bottom of your screens. And you can also use the chat function to send in questions and comments, which we'll monitor. So please send in your questions as you think of them, and then I'll bring them into the Q&A and the discussion with our authors and experts. So without further ado, let's move to the first presentation, which is a scene setter. And I'm delighted to introduce our first speaker, Dr. Matthew Ives. Matt is an economist and a complex systems modeler, and also a research associate at the Institute for New Economic Thinking at Oxford University. And his research focuses on developing strategies for a rapid and just transition to net zero. So if we could have Matt's slides up, please. Over to you, Matt.
Thank you, Anupama. What I'm having to present here is about a decade's worth of research, so I'm going to have to fly through it, and I'm going to have to show you some graphs, but graphs are science and science is cool. And plus, because this is empirically grounded work, so the way to show it is through the graphs, but hopefully it's going to be compelling enough for you. My co-authors on this are Professor Doane Farmer and Rupert Way and Penny Mealy, who have done a good portion of this work Doan Farm in particular, on that technological trends. Next slide, please. Just a quick overview. I'll be giving you an idea of what decision makers, next slide, please, are being taught about climate change strategies. Am I cutting out, am I?
Yeah, Matt, you cut out briefly there.
Okay, sorry. Okay, so I'm just going to talk about decarbonisation strategies and what people are being told by the IPCC modelling and what we think might be wrong with it, and perhaps a new perspective on it. You see the emissions going up there, the black line for over the past 40 years. And if we continue on that trajectory, we get into that above 4 degrees, catastrophic warming.
So Matt, I think you've cut out again. So could I suggest that you switch off your video perhaps, and then maybe we can get a better sound?
I think it's my side. I'm sorry about this. So it's not working?
It is, Matt, and maybe if you switch off your video, that might improve the connection.
That's
So
a good
maybe we
idea.
could try doing that. Yeah.
Yep. Okay, so the problem we have is the less than 2 degree scenarios there, that if you, in these climate models, the way you get to less than 2 degrees and turn the economy around is basically put on a carbon tax on the global economy. That results in economic growth being diminished, which also results in emissions being reduced. It results in less energy being used, which also results in less emissions. But then it also incentivizes investment in clean technology. And in a lot of these models, the technology of choice is carbon capture and storage. But because that's a piece of kit that you add on to your generation of electricity, that's an added expense. So electricity in these scenarios are likely to be more expensive. What's wrong with that perspective? Next slide, please. And next slide again. One key problem is that these models have not done a very good job of projecting future costs of very important clean energy technologies such as solar, wind, batteries, and electrolyzers for hydrogen production. You see there on the graph the actual costs of solar PV coming down through time. That's on a logarithmic scale. So that's exponential decline, as Tim was alluding to, that these exponential change in the system is what we're seeing with these technologies in particular. And the other lines you see there are the World Energy Outlook projections from the International Energy Agency. And just to give you an idea of how wrong they have got it in the past, that 2001 projection, in 2020, they projected that the cost would be $700 per megawatt hour, but in actual fact, it ended up at 70, an order of magnitude difference. And what you'll see is that all those lines are on the right-hand side of that actual. None of them are overly optimistic. And if you've got straight lines, as you can see there on the that logarithmic scale, it means you've got exponential change in the system. And usually that means in a complex system, you've got feedback dynamics. And one important one that I'm going to talk about is learning by doing, that when you deploy more of a technology, the cost comes down. And when the cost comes down, people demand more and you deploy more. Next slide, please. So what's an alternative perspective? Well, it's centered on that. And that is, if you were get one takeaway and we'll look at one graph, this is the one I want to focus on, because this is really tells the story. There in the brown, black and gray, those lines on the left-hand side are the costs of fossil fuels over the last 140 years. And what you can see is they haven't changed much, inflation adjusted. In contrast, have a look at solar in the gold there, that's come down more than 3 orders of magnitude, so 1,000-fold difference. And you've also got wind in blue, electrolyzers in green, and batteries in purple, and magenta going slightly up, but all those others, the magenta being nuclear. And on the right-hand side, you've got deployment, and that's the deployment of these technologies. Look at the gold and green and blue. They've all been going up in a straight line, again on a logarithmic graph, which means you've got exponential growth. So the question is, what happens if that exponential growth continues? And that's what we looked at. Next slide, please. But first, you've got to understand what are behind these trends. And that's the work that Doan Farm has been involved in over decades, looking at technological trends, two key points to be made. On the left-hand side there, you see that manufactured goods over a long period of time, the percentage that they've changed in their costs, inflation adjusted. And you can see most of the technologies around.
Okay, I think we've lost Matt again. We'll wait for a couple of minutes to see if he comes.
Drastically in their costs. Sorry?
Go ahead, Matt. You cut out for a second.
On the right-hand side, you see that how consistent those cost declines can be. If you look at television there at the bottom, you can see year on year the costs have been declining. So not all technologies are the same, and the trends are quite consistent. Next slide, please. That alludes to empirical laws, and there are two of them that work quite well on a range of technologies. Moore's law, which is associated with transistors, and an older law, Wright's law, which is associated with experience. So cumulative production of units. So when you double the number of units that you produce, you get your costs come down a certain percentage. And both laws, you can see, work quite well. The reason why we use Wright's law is because it has policy implications. The more you invest in these technologies, the more their costs come down. Next slide, please. And what Doan did was to reformulate Wright's law so that you can actually make predictions based on it. He validated over 50 technologies and developed a method where you can come up with reliable error bars on our predictions. So unlike the point projections of the IEA, which have no error bars associated with them, and the IPCC error bars associated with our predictions, we are making reliable predictions. And you can see in the white dots how those predictions have fared through time for solar PV. Next slide, please. And what we did was build a global energy model and applied that to global energy systems. And in particular, we replaced the fossil fuel system on the left-hand side, that's no transition, to a fast transition to renewables, batteries, electrolyzers for hydrogen. And basically, with those technologies, you can replace the entire fossil fuel system. And we did that, and we looked at, well, what does that imply? Next slide, please. So just projecting those deployment of those technologies, an extra 10 years, continuing the trends from the past for just 10 more years, we get a dramatic change in the energy system. We get emissions down to 80% of what they were by 2040 and down to close to zero by 2050. So a non-linear change to the system. Next slide, please. And the big kicker is that we found, because of those cost declines, the predicted savings are in the order of about 12 trillion. That's actually quite a conservative estimate because we were deliberately conservative. So you can solve and save money doing it. We should be doing this anyway. So next slide and the conclusions, please. So the take-home message, contrast this to what I showed first, that a fast transition to net zero for the energy system doesn't necessarily require any reduction in economic growth or energy use. Energy efficiency is a good idea. It'll make our solution even cheaper. We don't require any carbon capture and storage. You might need it for some of those parts of the system that are hard to abate. We only do the energy system there.
All right, I think, Matt, we've lost you again. This time, I think
the economics can drive the transition, and the risks and opportunities are there. And that's what Zac and Alex are going to be talking about in the context of China and India. Thank you.
Brilliant. Thanks very much, Matt, for that terrific presentation, which kind of sets the scene for the rest of this discussion. So I'd like to now move on to our second presenter, who is Alex Clark, who recently completed his PhD at the Smith School of Enterprise and the Environment at Oxford University. And he focused on the role of state-owned companies in the power sector globally and in China in particular. So the research that he's presenting today looks at just transitions and policy options for coal phase-out. I have to say that his other doctoral work looks at the economics of coal investments in state-owned economies and early retirement options for China's overseas coal fleet. And Alex, I think you're currently research director at Asset Impact, which is a data provider on carbon emitting assets in the real economy. So we have your slides on screen, and over to you, Alex.
Thank you very much, Anupama. I should also, before diving in, and I'll get started very quickly, is to thank my co-author on the full paper, Wei-Rong Zhang, as well as Anupama for putting a lot of work into making this accessible for a policy audience. Next slide, please. So just to set the scene on China, a lot of you will be aware of the broad parameters, but China has committed to peaking emissions before 2030, reaching carbon neutrality by 2060, and actually starting to, in its language, phase down emissions from the coal sector after 2025 in the 5-year plan between 2025 and 2030. Now, this is an enormous challenge that's so far off the scale of what most Western economies are dealing with that it's almost hard to imagine. On top of that, the implementation pathways and the specifics of them are still quite unclear. And Global Energy Monitor's analysis, along with the Centre for Clean Air, are finding that power capacity approvals at the moment in China are at their highest for several years and may yet still keep rising. Even with massive expansion, unprecedented expansion of carbon capture and storage, which, as Matt explained, is not necessarily a good idea when you have clean alternatives, the thermal coal sector, meaning coal power sector in China, will have to shrink by at least 90% by 2050 for its national targets to be met. And this will generate stranded assets, but it'll also have an impact on employment and tax revenue linked to coal, which is the subject of this study. Next slide, please. Very briefly, what we did was to take asset level facility data on coal plants and coal mines, and link them together using a simulated coal transportation network based on the distances between those 2 points, and then overlaid data on employment and tax revenues based on this network. Following that, we apply a range of different scenarios, which I'll get into in a second, which look at both the national effects and the regional effects of coal phase out in China on employment and the net fiscal contribution of coal to the exchequer. It's just important to note from this, there's a lot going on in this map on the bottom left here, but the key message that I'll get back to at the end is that effectively you've got 4 provinces supplying 3/4 of China's coal, and 3 of those provinces are responsible for over 90% of inter-provincial trade in coal. I'll explain why that's relevant in a second. Next slide, please. So just to go into the findings, we can discuss them more in the Q&A. But the key finding on the side of employment is that employment in the coal sector will keep falling even without stricter climate policies. And most of those jobs are in mines. The graph on the left here shows you how it's broken down into jobs in mining, transport, and within coal plants. But you can see that mining accounts for the majority of those jobs. And actually, employment in coal mines in China has already halved just in 6 years from 2014 to 2020. So even in the most ambitious climate policy scenarios in China, that rate is not going to be exceeded. In the baseline scenario, which is very conservative, total employment is 30% down by 2030 across plants, mines, and transport, and it halves by the late 2030s. Most of the job losses are in mining, and jobs in transportation and coal plants start declining as plant closures begin to accelerate, which in the baseline scenario is in the late 2030s. And the key driver is actually not climate policy, but improving productivity in coal mines, which has been 8% a year historically. And to be conservative, we assumed 5% a year in our model. And the employment impact of productivity gains are higher in those provinces with less technologically advanced and more labor-intensive mining. And there's a huge variation across the different provinces within China. Next slide, please. On the fiscal side, we find cautiously, bearing in mind that data is often not complete, is that coal phase out may be net positive for China's public finances. So just to give you a quick idea, the taxes associated with the coal sector are raised both from capital and labour, skewed heavily towards capital, and they accrue to provincial and national governments respectively. Interestingly, the total amounts accruing to provincial and national governments are very close, as you can see from the graphic here. They peak in the 2020s and then decline, and that decline accelerates as coal plants start to retire because the tax base is very heavily skewed towards capital. We find that tax revenue peaks from the thermal coal sector, based on our estimates, peaks at about £40 billion or $50 billion equivalent annually. But we also find that subsidies, which are estimated on a national level rather than from the bottom up, like tax revenue, are estimated at much higher than that, almost 50% higher, and that's without including climate damages and climate externalities. So even without accounting for the impact of climate change, it's quite possible that coal is already a drain on China's public finances. Next slide, please. I think I'll just have to be very brief in the last couple of slides, but just all this says is that more aggressive climate policies, and by extension less aggressive climate policies, don't really change the picture. They just shift it forward or backward in time. Next slide, please. So what are the implications for China's transition policies? You're looking at about 2.5 million jobs at risk and 50 billion pounds equivalent in tax revenue. Sorry, that should be dollars at risk. So where do the workers go and how are the tax revenues replaced? It may be worth extending and improving existing measures, which include China's Industrial Special Fund, which already exists to handle previous job losses in the coal sector. But there is a need to act quickly, particularly as the coal transition accelerates, on focusing on key coal-producing provinces, a greater institutional focus on national and regional coordination, both governmental and through the network of state-owned enterprises, and more strategic integration into the overall plans for sectors beyond power and how these might interact with coal phase-out. And then finally, on new measures that might be worth taking, there's certainly a need to focus on redistribution and institutional coordination, perhaps balancing gains in less exposed provinces that are more able to move away from coal without a severe impact on their tax base to cushion the impact in the coal-producing ones like the Inner Mongolias. We also find that a transition towards consumption-based taxes in the long term can help to establish a stable base of tax revenue from clean assets alongside increased electricity demand. And there's a need to potentially make further transition support to subnational governments conditional on more detailed transition plans. Next slide, please. This is just a quick explanation of scenario settings, which is really just here in case there are questions relating to it. But effectively what we do in the model is to vary the number of years that a plant is assumed to be in operation. So there's plenty of scope to introduce more sophisticated analysis. But I think I'm just about at time, so I'll stop there. And thank you for listening.
Thanks very much, Alex, and thanks for keeping to perfect time on that. And very strong messages coming out of that, particularly your conclusion that it doesn't make a difference if climate policies are more or less aggressive. There's already a trend towards coal phase out. So I'm now delighted to bring in our first expert discussant into this discussion, and that's Connor Gask from the International Energy Agency. So Connor is currently an energy efficiency analyst at the IEA, where he focuses on policy analysis and capacity building in China and Africa, including promoting actions on the demand side that can support inclusive, people-centered energy transitions. Prior to this, he led engagement with Chinese partners on renewable energy and power market reforms at the British Embassy in Beijing, including working to promote a clean energy transition with state-owned utilities and grid companies. So Connor, you're obviously very, very deeply involved in the granularity of what's going on in China. Could you give us some reflections on what you've heard from Alex and from his presentation?
Thanks, Anupama, and it's great to be involved with EEIST again, first of all, and great to see some old friends, and Alex as well. Thank you again for your overview of the work you've been doing and your continued research in this area, which I think gives us all a very detailed update kind of every six months or every year on where things kind of stand in terms of potential for coal phase out in China. As Anupama mentioned, I mainly focus on the demand side, but happy to share maybe a few more insights from the broader analysis that we've been doing at IEA today. But maybe just to put a plug in there for our energy efficiency division, in that we're trying as best as we can to work with policymakers in China to drive or increase the focus on demand side investment in energy efficiency, but also power system flexibility as a way to both taper demand for energy, but also to create new opportunities for investment, job creation at a local level, which I think as Alex kind of, as you kind of elaborated on in your research, the issue of this transition in terms of employment opportunities, but also reskilling and reallocating of jobs at a local level is something which is both economically and politically challenging in China, but also elsewhere. I maybe just wanted to reference as well that recently our analysis found that we expect fossil fuel use to peak globally by the end of this decade. And I think that's reflected as well in the presentation from Alex and Matt and the work that you do in looking at multiplier effects and exponential change. And this idea of learning by doing is something which is really important in terms of being able to capture those effects in our own analysis and modeling, and it's something which we're continually working on doing. I think it's also worth mentioning that last year was the second year in a row where we saw an all-time high in coal-fired generation, increasing by 2%. So there is work that needs to be done, and our IEA net zero emissions scenario requires that all unabated coal generation ends by 2040. But this calls for immediate reductions and global decline in unabated coal-fired generation of around 55% by 2030. So again, to see that outline of the different forecasts and models, Alex, that you've been using in your analysis, it was very interesting to see in the most optimistic scenario some quite high numbers for either cancellation or phasing out of coal projects much earlier than expected. And it would be interesting again to get your insights on where some of the risks associated with that lie. And I know I'm limited on time, but maybe just one final plug is obviously looking at the role of inclusive transitions and the agency. It's an area that we haven't looked at so much in the past, but we've been expanded our focus on employment issues over the last few years and looking at topics of jobs and skills by developing an employment modeling approach in our World Employment Report. But again, I think there would be colleagues from across the agency who can't be here today who would be very keen to speak with you and maybe share ideas in a bit more detail. But I'll leave it there.
Thanks very much, Connor. I wonder whether, Alex, you'd like to come back on one of Connor's points there on the risks related to all of those scenarios. But it sounds, I don't know, Connor, whether it sounds like what you're hearing from Alex is broadly in line with what the granularity of the work is and of the modeling that you're looking at is. But Alex, perhaps you could come in on and give us a few sort of thoughts on.
Thank you. Yes, certainly will. And thank you, Connor, for your comments. I think I'll just briefly touch on the challenge of replacing coal jobs with green ones. It's an interesting story in China because the renewable sector is still growing at awe-inspiring rates. But a lot of that growth is capital intensive, meaning that it might employ a lot of people in the short term, but it's not necessarily clear how those jobs will remain in the long term. And it's also the case that the locations and timing of jobs lost in brown sectors, which can be coal, but also other sectors in transition, is not necessarily the same as where new jobs will appear. So it's probably fair to say that there's a clear leadership role for government there, both in identifying adjacent clean industries where skills can be repurposed, at least with a minimum of reskilling and retraining. And there are colleagues at Oxford who've been doing excellent work on that in Brazil, as well as a couple of other jurisdictions, although China is challenging for data reasons. And that these should be, like a lot of the policy prescriptions within the EEIST program, these should be adjusted over time. And in the Chinese context, potentially operate both as standalone government programs, retraining centers and so on, but also be integrated into the state-owned sector through SOEs, both at the national level and the provincial level, since they're almost two parallel systems of economic activity. Thanks.
Great, thanks a lot. I don't know, Connor, if you want to come back on any of those points at all.
I mean, I think, Alex, you gave a very in-depth answer, and it was interesting that you mentioned again the role of state-owned enterprises, and you mentioned also CESAC in your presentation. So again, maybe a question to you on when it comes to China in particular, the kind of dominance of the state-owned sector in coal power generation, but also coal mining, where you maybe see that as either a opportunity in terms of the levers that the Chinese government can work with to foster this transition, or where you might see that presenting a barrier?
Yes, I think coordination and figuring out how to move from where things currently are to where they need to be in terms of helping the state and the enterprises it controls play the most productive role they can in the transition is extremely difficult. And from those of us working from the outside, as I have been mostly with this project, it's difficult to keep your finger on the pulse of what's changing, because it's clear that there is a lot of changing. So understanding institutional configuration is very, very difficult. There have been a couple of revealing events which you'll be familiar with, but perhaps some of our listeners won't, which is a fairly public admonishment of the National Energy Administration's role in approving new coal plants by the Central Environmental Inspection Team, which had a mandate from the State Council at the national level, which is fairly unprecedented. And it's difficult to say what's happened since, but there's clearly a lot of tension between the clearly articulated national policy goals and the actual implementation, whether it's through regional governments and also through SOEs. The last thing I'll say is that the big five centrally owned SOEs that operate in the power sector, largely speaking, operate on the national level, and they can implement plans, not necessarily with the need to coordinate with regional officials or development plans. So at the same time as being asked to come up with, transition related development plans, it's also the case that regional planners don't necessarily have the authority that they need, or even the dialogue that they need to make sure that the transition is politically sustainable, which is something that the focus on employment and tax in this paper tries to highlight.
Great, Alex. I have some questions coming in on that, and I'd just like to remind our audience to send in your questions as well on the Q&A. Perhaps that's something we can get to during the discussion as well. But thank you both, Connor and Alex, for that exchange on the presentation. We'll come back to that again in the Q&A part and the discussion part of this webinar. But I think it's possibly time now to move on to our next presenter, who's Dr. Zac Cesaro, who was a PhD researcher at the Department of Engineering Science in Oxford University, focused on modeling the role of hydrogen and ammonia in future energy systems. Zac currently works in research and development on the topic of ammonia cracking at Siemens Energy, but he's presenting today on the research conducted during his PhD. So Zac, we have your slides up on screen. Over to you.
Thanks, Anupama. Okay, so as you mentioned, I'm going to be talking about hydrogen and ammonia in the context of the Indian energy system. Next slide, please. So first, I'm just going to set the scene a little bit about India's energy transition and the role of in green hydrogen and ammonia in that context. Next slide, please. So India is going to be a very central part of the energy transition on a global scale. I'm plugging the IEA a few times here. A quote which I think sums it up well is, whichever way the global energy economy evolves from here, India will be firmly at its center. It's forecast to have the single largest increase in energy demand, as well as CO2 emissions by any country from now until 2040. A big part of that is urbanization. So it's adding a city the size of Los Angeles each year from now until 2040. And that kind of statement is quite hard to imagine, but what goes along with that is infrastructure, cement, steel, appliances, vehicles, everything alongside that. In the same time, there's this massive growth and transition going on. So India has targeted 50% of energy installed capacity to be from non-fossil fuel sources by 2030 and a net zero target by 2070. In summary, it's rapid economic growth, rapid urbanization, rapid industrialization to support that urbanization, and rapid decarbonization all at the same time. So it's quite an interesting case study to look at from an energy perspective. It's really at the center. Next slide, please. And on hydrogen, India's announced a national green hydrogen mission, which is targeting 5 million tons of green hydrogen by 2030, largely for the ammonia sector, as well as some for the other chemical sectors, like refining, steel, mobility, and shipping. The other objectives of the mission are to establish India as a global hub for manufacturing electrolyzers, reduce imports, so particularly in the ammonia sector, which is for fertilizer today. India is the world's largest importer of fossil fuel-based ammonia, and it imports LNG to make about half of the ammonia that is domestically produced. So huge import dependence on things that can be replaced by green hydrogen. Beyond imports, India is also targeting with this mission to capture about 10% of the global hydrogen and ammonia export market. So being able to export surplus hydrogen from India. Next slide, please. And one of the first things we did was just to look at the scale of this emerging hydrogen, green hydrogen and ammonia sector. And this graph looks at the amount of electricity that would be needed to meet those demands for hydrogen and ammonia. And what you see over time in the yellow line is that basically ends up being around a quarter, 25% of India's electricity needs to be going into electrolyzers to make hydrogen, or the next step, make ammonia. And that is, if you click through, I think there's a few bubbles here. This is only assuming around 50% decarbonization of steel and fertilizer. So it could be quite a bit larger, as well as not including hydrogen for aviation, which almost certainly will have some kind of hydrogen involved. And I think one of the key points here is that this, just looking at this from a pure numbers base, this is a very large part of the system that's going to grow basically from nothing today, and account for a huge part of the energy system. So it's not one that can really be ignored when you're looking at the transition. Next slide, please. One of the questions, and this is one of the focuses of our work, is looking at how you build out this huge hydrogen sector. And one big question, we've looked at the two extremes, are do you build these electrolyzers and hydrogen and ammonia plants as islands, so they have their own renewables attached to them, but they're completely disconnected from the grid? Or do you build them in connection with the grid, in which they can give and take electricity as needed in a very coupled way with the grid? Now, this is an interesting question, particularly in the context of India, although I would argue it's interesting in all of the different countries and energy systems around the world. But in India, captive power, which is basically islanded systems, has been historically the way that industry has gone. So in India today, around 20% of India's electricity generation is off the grid or barely connected to the grid, which is in what's called captive power plants for the industrial users who don't want to connect to the grid for a variety of reasons, things around reliability, connection charges, and high prices. And if there's quite different systems if this huge hydrogen economy goes one of these two different ways. Next slide, please. So I'm going to briefly touch on some of the methodology we use to look at this particular question. Next slide. And of course, if you want more details, please refer to the paper and the policy brief as well. So we took a sort of traditional energy system model of the electricity grid in India and added three main additions to it in line with the EEIST principles. So the first is a much more dynamic modeling of hydrogen and ammonia. Most models today exclude hydrogen and ammonia really on any country. I think some are starting to include them, but often have a very static demand. So this means that those plants can't turn down. There's no give and take with the grid. And this misses a huge opportunity based on our findings, which I'll present later on, that this misses a big opportunity of how the future system could look. The second improvement is around technology cost and using learning curves, which Matt mentioned in a previous presentation. And then the final element that we added was including system resilience. So most energy system models today will use 1 year of weather data, what's called typical meteorological year. And of course, when you're moving to a system that's very heavily based on solar and wind, and you have a bad wind year, you need to build a system that's resilient to that bad wind year or bad wind 2-week period. And what we did was take 10 years of granular weather data in India to build this model. So it not only has to meet the energy demand in a particular year, but it has to manage for all 10 years of the weather data. Next slide, please. And finally, just to talk through the results, next slide. We found that grid integration, so of these two options of islanded or grid integration, we found grid integration is a much better system design. It improves affordability foremost. So you have a lot less curtailment because of all these electrolyzers connected to the grid, being able to take energy at times of surplus. So around 20% less curtailment. You reduced that nominally, actually, just to put it into proper numbers, is around 200 to 300 gigawatts less solar and wind that needs to be installed, which is huge. We also found that it reduces the levelized cost of hydrogen and ammonia. So actually, this is better for industry as well. Their hydrogen and ammonia would be cheaper if they connected to the grid in our scenarios. And overall, the system cost is down by about 5%. The second element is around security of supply and resilience. So one of our really interesting findings was that, and it's shown in this graph here, is that ammonia is produced, particularly ammonia, because it's much easier to store over long durations. It's produced in a seasonal pattern, which is found to be a cost optimal way of doing it. And between different years, the same week might produce very different amounts of ammonia. So if you look at August there, you see some years where you're basically hardly making any ammonia because the weather, for example, wind is quite low in that year. Whereas other years, your ammonia plants are running almost full out because you have a lot of wind at that point in that year. And we find that this flexibility really provides a lot of benefits to the system and allows it to manage these years of different levels of renewables. Next slide, please. Yeah, you can just click through those. Thanks. Final slide. So I think our recommendations based out on this research, the first is that it's suggesting grid connectivity is something that should be encouraged from a policy standpoint. Again, historically in India, industry has preferred to be islanded. And so this is a little bit of a policy shift or needs to be nudged towards that direction. And then the second thing I would say that's coming out of our work is me as a modeler would say everyone needs to improve their models. I don't think enough models are looking at this type of scale of hydrogen and ammonia when they really need to be, and the dynamic coupling of them with the grid. And I'm really interested to see other models start to look at the same question and to see what kind of results they get. Thank you.
Thanks very much, Zac, for that very detailed presentation. And I'm delighted to say that I think we have the perfect person here to discuss this policy brief and this paper. So I'm delighted to introduce Dr. Guncha Munjal, who is manager for the hydrogen team in the Sustainable Cities and Transport Program at WRI India. Dr. Munjal is based in Delhi and looks after projects relating to hydrogen production, storage, and regulations. Prior to joining WRI, Dr. Munjal was working as a scientist on hydrogen at the National Thermal Power Corporation, or NTPC, Energy Technology Research Alliance, which is a research and development arm of NTPC. Dr. Munjal completed her doctorate from chemical engineering at IIT Delhi, the Indian Institute of Technology, and her work has been presented widely at many conferences. So thanks very much for joining us, Dr. Munjal, Guncha. So I'd like to bring you in at this point, and perhaps you could give us some reflections on what Zac has just presented, particularly given your work with the Green Hydrogen Mission and your understanding of the priorities of the National Green Hydrogen Mission.
Well, thank you, Anupama. Thanks, Zac, for the presentation. Well, as truly said by Zac, that by India has recently launched Green Hydrogen Mission in January 2023, and aims for production of green hydrogen as a target of 5 million metric tons, which is huge. And for producing that much of green hydrogen, you need 60 to 65 gigawatt of electrolyzer capacity. And in turn, if we calculate it by keeping 25% CUF, we need 125 gigawatt of renewable energy supplies, which in itself is a challenge for India to observe, because right now, for example, India has a total capacity of around 425 gigawatt capacity, and out of which 31% is the renewable energy capacity. So coming up with a new renewable energy sources completely for producing green hydrogen in itself is a challenge. Other than that, the grid integration with the new ecosystem of hydrogen developing in itself is another challenge, where I think the model which is developed by the Zac will be very beneficial. It is important to understand the challenges and benefits of the integrated power energy systems to come up with this huge amount of green hydrogen. So I feel that the model which is developed is very interesting, and it will give very good inputs to the policymakers. If we talk about the challenges which you have mentioned about the green hydrogen missions in India for implementation, I believe there are three important challenges, and I'll discuss those three challenges. So the first challenge, I feel, is the availability of renewable energy at a reasonable price. to make green hydrogen economically viable. The green hydrogen ecosystem will not uptake until and unless its cost is comparable to that of the gray hydrogen. And the cost if we calculate the levelized cost of hydrogen or as a matter of levelized cost of ammonia, the maximum price, that is 65 to 70%, is the renewable energy cost. Okay, so I believe that when the renewable energy cost will come down, the cost of the green hydrogen will by default become economical. And at the same time, India should encourage the domestic electrolyzer manufacturing, to increase its domestic electrolyzer manufacturing capacity, which is happening by, like, Government of India has recently come up with a production linked incentive, which is actually, so from the $2.2 billion which is mentioned in National Green Hydrogen, around 88% is dedicated for the domestic manufacturing of electrolyzer or production of green hydrogen. Okay, so India has recently come up with the scheme which is called as SITE, the PLI scheme for producing electrolyzer. And yes, it is in the rollout. And I think it is very important if we want to achieve this particular target. The second important thing which I feel is a challenge is a supportive policy framework. As there is a growth in any new upcoming industry, requires government to incentivize supply and create demand through policy interventions, which has to happen in each and every country, not in India, but I think it has to happen in every country. And third thing, which I believe is important, is support research and development, along with doing all these things, along with giving policy benefits, along with giving, coming up with PLI schemes and all those things. We should also, government should also keep in focus that simultaneously support to research, support to pilot scales, and support on how hydrogen clusters or hydrogen valleys can be formed, and where it can be beneficial not only to economically but also to the regional, like specific regional areas of India, which will benefit at a larger scale. So I believe these three important challenges are there if we want to implement the National Green Hydrogen Mission successfully. But yes, there are many other interventions or measures which can be taken. So maybe I'll ask Zac again to, what else, or what incentives, or what collaborations, or what R&D measures, can take place with, every country is coming up with national hydrogen strategies.
Zac, would you like to take that and give us your thoughts on that?
Sure. I had a few thoughts on just some of the things you mentioned and some I wanted to underline. So I think the scale, that it's such a big scale of renewable needed for the electrolyzers to come online, even to meet the 2030 target, which in the grand scheme of things is actually quite small. It looks big today, but when you look out to 2050, it's just the beginning. I think that point, one of the points I would hope to highlight is, like, that's only going to continue, that you have such a big need. The scale of it is just going to keep getting bigger, of how much renewables you need to make hydrogen. That's not going to avoid the fact that we're going to need to make a lot of hydrogen. And that scale also presents opportunity to think about how all those things coming onto the grid, if they did come onto the grid, could really benefit the grid of the future and redesign it. I wanted to highlight one element of cost, which you mentioned as a challenge in reaching cost parity with gray hydrogen today. One element is historically the price of ammonia, which I know a little bit better, has been, because it's a globally traded commodity, has been somewhere between $200 per ton and $600 per ton. After Russia invaded Ukraine, it went up to $1,800 a ton in the UK locally when I was getting quotes. And just green can certainly be way under that. And one of the abilities for India, I think its unique position, is that it can really focus on domestic demand, particularly for ammonia, as an off-taker. And that highlighted one of your other points around this policy framework to incentivize demand, that to reduce LNG imports that are going into ammonia production, as an example, really would be a benefit for India. And I think the cost benefit would work out very, very close to working out already. I mean, of course, you have to assume a natural gas price, which is anyone's guess. But yeah, and I think, now I've forgotten. Sorry, what was the main question you had?
At the global scale, what can we, what measures or collaborations or R&D efforts can help these national hydrogen strategies to come into the reality?
So I think actually focusing on the ammonia industry could be a good one, because there's only about, I think, 4 ammonia licensors in the whole world. So there's not very many companies that actually make ammonia or have the technology to produce ammonia. And India is such a big market for it that all of the global producers are quite interested in India for ammonia production. So I think, again, focusing on that sector as like a really good foothold for India might be a good way to attract that international R&D, particularly around green ammonia, and which will bring the electrolyzer manufacturers behind them, I think.
Thanks very much, Zach, for that. And I think we sort of are coming up to the hour, so I'd like to sort of open it up to more questions and discussion. We do have some audience questions coming in as well, so maybe this is a good time to bring everyone back on screen. And perhaps, so we've got a lot of questions, but perhaps I can kick off with just one overarching question, which maybe I'll pose to Professor Tim Lenton. So Tim, I mean, this is the results from the modeling, and everything that we've heard suggests that in some cases, policymakers should be directing their efforts to speed up the transition to net zero. And yet this is sort of the opposite of what some governments appear to be doing. So where should governments be adopting new economic modeling, and how can it be used to change the narrative? And if you could give us like a succinct answer, your thoughts on that, that would be great.
I'll diplomatically put question after the UK Prime Minister's rowback yesterday on the net zero vehicle emissions mandate. So, I mean, the key point that you've hinted at is we know something from these studies and other studies conducted in the EEIST project of how powerful policy can be in further accelerating what's already an S-curve transition. We haven't dwelt specifically in today's discussion on the EV story, but it's a more general rule that's pertinent to the ammonia and green hydrogen question that we've just been discussing with Zach, that mandates to, for example, introduce progressively increasing amount of green hydrogen or green ammonia into fertilizer, for example. We're confident that these are really cost-effective as well as acceleration-effective policy moves. So yeah, I mean, the whole thrust of our project, as the audience will be appreciating, is to show that this kind of modelling can provide actionable and useful policy advice in the collective global pursuit of getting to net zero as fast and effectively as we all can, whereas conventional economic modelling, neoclassical, is often found wanting for the simple reason that it has a different philosophical view of the economy, and it's concerned with maintaining the current equilibrium and assuming that there are only small or no deviations from it. So we're excited, and I'm excited to listen to the team today. We're excited to be able to offer this and to be engaging with policymakers across China, India, and we haven't talked about it today, but also Brazil, to bring some of this thinking into practice. And the proof, as ever, will be in the pudding. So yeah, we're here really to offer that useful advice to policy. Thanks.
Great, and exactly, and I think there are parts of government which could adopt this modeling methodology to inform their decision making. We've had a very interesting question come in, which is about safe hydrogen storage, and I'm not sure if any of the panelists want to volunteer to take that question on. But the question is, what do you think the conditions are for safe hydrogen storage, especially in Central Eastern Europe? And I think, yes, is anyone, can I have a volunteer from among the panelists? If not, perhaps we could bring, all right, Zach, go ahead.
Yeah, I don't know specifically the one question that comes to mind is I don't know the geology of that region of the world. The big ways of storing hydrogen are, it basically has to be either some underground storage, so a salt cavern or a rock cavern, or in the form of another molecule like methanol or ammonia. Liquid hydrogen is potentially something that will be around at scale in the next maybe a decade. It's coming a bit slower. It's starting from a lower starting point. But those are kind of the main ways of storing. And I think all of those can be done in very safe ways. Of course, we need to treat them as industrial chemical storage as they are. Some we have many existing standards on, like methanol and ammonia. Others are a bit newer, like liquid hydrogen or salt cavern storage. But we still have salt caverns around the world that do store hydrogen. So there's some experience in all of them that I think it can be done in a safe way.
Great. Thanks a lot, Zac. And yes, please, to the questioner, please feel free to follow up with us as well when you've read the brief. I'd like to sort of come back to China because we've had some interesting feedback on the policy brief. And perhaps, Alex, I can bring you in at this point, and maybe Connor can give us a bit of his reflection on this. CCS and CCUS are obviously talking points in China. So did you look at those in your scenarios? And what difference do you think that might make to your results if China develops new CCS capacity?
Yeah, that's a great question. So just for those who are not aware, but I'm assuming most attendees are, CCS is carbon capture and storage, and the U is utilization. So we did not model CCS explicitly, but the projections and the calibration that we used for power generation trajectories were based on models that did allow for CCS. So a model that we didn't use, but is quite useful as well, is one that's managed by Tsinghua University, and it finds that under a 2 Celsius scenario, and this was also modeling that was used directly to inform the government's major decisions 2 years ago, they find that coal power decline over 90% under a 2C scenario by 2050, even with half of that coming from CCS. And in a 1.5 degree scenario, it's about the same decline, except 90% is coming from CCS. So it's not to say that these models say there's not going to be such thing as CCS. And even in both of those cases, it's well known that most models tend to be very optimistic, especially if you're looking backwards at historical rates of deployment on how quickly CCS can be deployed. So, you know, a priori, it's not necessarily justified to assume, you know, a high level of deployment. There are a couple of caveats, one of which is that this could be quite a different story for non-thermal coal use, simply because it's much more difficult, much more challenging, and depends a lot more on enlightened policy, I suppose, and policy support to replace coal in steel and cement manufacturing. In China, this is a particular problem because most of it's steel mills and not electric arc furnaces, they're blast furnaces. They're very difficult to deal with, but there are, as I'm sure Zac is thinking right now, there are certainly ways of getting around that. There's the same is true for combined heat and power. So in the baseline scenario, so by the same I mean that you know, it's worthwhile asking questions about combined heat and power, which is also used quite extensively in China. But in our modeling, all we're doing is assuming that all existing plants are closed after the end of their planned lifetimes, and the only way this would be affected by the greater use of combined heat and power is if it led to the construction of many new plants that weren't previously planned, which is within the realms of possibility as we're seeing right now. But just to summarize, you know, CCS does not really make all that much of a difference based on our modeling.
Thanks a lot, Alex. And we're rapidly coming to the end of this session. I think some of our speakers have a hard stop there. I just want to take the very last minute to quickly bring in Connor to give in just a few seconds of your reaction to Alex's point on CCS, and then Dr. Munjal, I'd like to come to you for the last word.
Thanks, Anupama, and I couldn't claim myself to be an expert in CCS, so maybe I'll maybe take a different angle on this, but obviously CCUS does play a role in IEA's modeling to some extent, and even in our net zero emissions scenario, there is an element of requirement for CCUS to be applied in systems, especially in China, but also in India as well, as parts of the kind of broader coal phase out program. I would say, you know, we would obviously, again, from an energy efficiency hat perspective, prefer that those investments go more towards expanding investments on the demand side. And there are opportunities that we're seeing in China. I think Alex mentioned in the steel sector, although it is a very difficult to electrify sector. We think, from what we're seeing in China in terms of some of the progress that's being made on installation of electric arc furnaces, but also on electrification and integration into the grid, that there could be multiplier effects from that perspective, where electrification of steel means that we don't need application of CCUS in the future. And China, as we know, is a country where we're able to develop economies of scale very quickly. But then looking as well on the heating side as well, we're looking a lot more into things such as heat pumps and whether there's opportunities for combination with the very rapid rollout of rooftop solar. And again, that presents an alternative area where investment could flow as opposed to CCUS. So maybe just a few comments there. I don't know whether they answered necessarily the question on CCUS, but we would always propose diverting attention to other areas for investment where it's possible.
Brilliant. Thanks a lot for that, Connor. And I think that's just a nice segue to a final point, final word from Guncha. Obviously, this is also an issue in India, but with the development of the green hydrogen ecosystem, do you think that will have a substantial impact on India's own plans around its grid operations planning and the coal sector? Could you give us just a few seconds on that?
Well, each and every country has a different grid operations. So with time only you'll get to know that how the gigawatt scales electrolyzers are affecting Europe's system and how the gigawatt scale electrolyzers are affecting the Indian grid system. But I think that huge balancing and grid network will be required if India wants to come up with this 5 million metric ton through 60 gigawatt of electrolyzer capacities. And the grid operations can't be ignored if we are combining gigawatt scale electrolyzers to come up, to the market. But I think it will take time. So initially, maybe the megawatt or kilowatt scales will do fine. But over the period of time, these things has to be, the proper simulations, proper mathematical models has to come up before integrating the gigawatt scale electrolyzers to the Indian grid system.
That's a great note, and perhaps that is what EEIST can contribute to in the end. So I'm sorry to say that we've completely come to the end of our time. We're about 3 minutes over time, but it's been a pleasure to moderate this session. So thank you to all of our speakers for their insights and to the audience for staying with us. You can read the policy briefs and access all of the underlying research on which they're based on the EEIST website. But thank you very much for joining us, and I hope you enjoy the rest of Climate Week in New York. Thank you and goodbye, everyone.